Hello class, welcome to Chapter 5, Integration. Here we focus on the definite integral. In the previous lecture, we saw extensively on how to chop down the given area into very, very thin rectangular slices so that when we add their areas together, we will eliminate overestimation, underestimation, and we can produce an area that's exact and not an approximate value, because we now have a way of getting infinite number of rectangles as opposed to a finite number of rectangles. And that idea we're still developing, but then we got the concept of how we could apply limit to Rayman sum. So limit as n approaches infinity to the Rayman sum helped us to obtain a near perfect measure of the area under the curve. So I cannot insist enough in saying that you really, really have to imagine these rectangles being very, very thin so that their base is almost negligible, because your rectangles are like lines. You really can't see the width for those rectangles. That's the kind of fineness with which you draw these rectangles. So you can only imagine this, right? And this is possible only if you had your number of rectangles going towards infinity. Infinite rectangles, then you can come back and say, yes, then it's possible to have these extremely thin rectangles. Therefore, when we apply limit to Rayman sum, and we know that Rayman sum is summation k 1 to infinity, 1 to n. You could use k or I. The book uses them interchangeably. This was the one we saw for Rayman sum, and if you remember xk with an asterisk, with a star, it tells us that you can choose any point in the interval. It doesn't have to be the left end point, the right end point, or the middle point, midpoint. It could be any point in the interval, and that's because your rectangles are so thin, it really doesn't matter where you pick your point. Yeah. All right, so this means the summation you see here for finite sums becomes the integral symbol. Remember, integral, the way we defined it was the collection of all antiderivatives. So this is all possibilities. This is for all possible. So this integral symbol then becomes for infinitesimal sum. we have kind of evolved, just like how in derivatives, limit of dq took on a new notation, either the prime notation or the dy over dx notation. Likewise, we now have integral as the new notation for limit of Rayman sum. And just as how we saw a number of rules that followed that helped us to find the derivative so quickly, right? So when we had to find the derivative of, say, x squared, we had to do the x plus h, f of x plus h minus f of x all over h. That limit of that dq is what we did to get the derivative originally, but once we got the rules, we simply did, derivative of x squared is 2x. We got that just because of those rules, right? Similarly, we have rules that will simplify our process, our integration process, and we've seen this before because we did the antiderivatives. And what you're learning now is basically this integral is your area, and we'll get to that. We'll try to make the connection soon. But what we're seeing is that this is integration that can be seen as antiderivatives. That's how we were introduced to this. But now we have a definite integral wherein you have lower limit of integration, upper limit of integration, and that carries a set of rules. So let's check those rules. So these are the rules satisfied by definite integrals. Now remember, I said the lower limit should always, the lower value should always be in the bottom of your integral sign, and the upper limit should be on the top, so that you say integral 0 to 1. You don't say integral 1 to 0. Just as how you would read any intervals, right? You say 2 to 3, you don't say 3 to 2. You always read from small to big. So in that sense, the order of integration is very important. And what this rule says is, if you have the order mixed up, if you went from B to A, if you went in the opposite direction, then that opposite is indicated by the negative, and where you adjust the limits properly so that the lower limit is on the bottom and the upper limit is on the top. So this order of integration rule adjusts it for you if you wrote the order incorrectly, or if the order was meant to be written that way in some circumstances, as we will see. Okay, so that's why it's very, very important that we consciously put the order in the way it should be. Zero width interval, the second one, there again it's true that if you took the integral from a to a, f of x dx, you didn't really move, right? What is integral f of x dx? It says, well, integral f of x dx is telling us that this is the area under the curve from a to b. So if you went from a to a, it just means you didn't go anywhere, right? So you were just standing at that point. So you really can't measure the area for a point, and that's what it means. So the area for such a point would be 0. Constant multiple, just like we saw in the summation, the finite sums rules as well. You pull out the constant because the whole thing is related to x, because x is the variable of integration. If you had any other variable like in this case k, that is considered as a constant. So even though it appears as a letter, the letter is considered to be constant because it is not your variable of integration. Sum and difference rule works. Additivity, as you can see, if you wanted to add integral a to b f of x dx to integral b to c f of x dx, going from a to b and then b to c for that same function, that means it's as if you went all the way from a to c, and that's what the additivity rule says. Then you have the max and the min. So this is basically coming from our, in fact we saw this roughly in average height, but I'll kind of explain that shortly. So what we have is, we looked at the max and the min formula previously, and so we draw this from there. Okay. Now we also have domination. Domination is if one function is bigger than the other function, like if f of x is greater than g of x, then it means the area under the curve for f of x will also be greater than the area under the curve of g of x, which is indicated by using the integral signs. In definite integral of a to b f of x dx is greater than or equal to definite integral a to b g of x dx. I have some pictures here to kind of depict these rules. So as you can see, zero width rule or interval, you did not move from a anywhere else, so you did not really span any area, so the area is 0. Constant multiple. Here's an example of how the blue graph is f of x and the yellow graph is 2 times f of x. So if you went 2 times above, the area for this, the area under the yellow curve, this whole thing, this whole, what do you say, orange shaded region, that also includes the blue. That whole region is the same as blue region times 2. Okay, that's what it means. Then we have the sum. So if you wanted to add the area, so if this is f of x and the g of x, f of x plus g of x would be the sum of the blue and the orange, which gives you the green. Don't think the green just stops just at the yellow. The green goes all the way down. Okay? It's the area under the curve up to the x-axis. So it's all the way down. You just can't see the different colors merging here, otherwise it would be confusing. And the additivity rule we saw, if you took the integral from a to b, which is the orange, and if you took the integral from b to c, which is the blue, it's the same as if you took the integral from a to c all the way included. So that's going to be orange plus blue. That's all the way. There's no break. Maximum minimum. This is somewhat like your squeeze theorem. This basically comes from that idea. Okay, so if you and it also comes from our extreme value theorem ideas, right? So all of these are kind of somewhere influencing it in the background. So you do have a minimum of f, the minimum point of the function. Yeah? As you can see, this is the minimum point of the function, and it's indicated here. And this is the maximum point of the function. So in fact, if you see EVT, if you recall EVT, extreme value theorem, if f is continuous on a closed interval AB, so that's what we have here, it's continuous on closed interval AB, then EVT guarantees an absolute minimum and an absolute maximum. And that is what we have here. So the absolute minimum will be the lowest value, and therefore it will be a value lesser than all other f of x's. And the maximum, absolute maximum will be the highest value, the highest y value for all among all the function values, and therefore that will be above other values. So basically, this is what we did. We said minimum value of f is less than or equal to f of x, which is less than or equal to maximum value of f, right? That was the idea of EVT, that your other values, function values, will be in between the min and the max. And so if you basically multiply by b minus a on all the 3 parts, you will get this. And so we can look at that derivation later when we look at one of the problems. And then domination. Domination, of course, says if blue graph is above the green, the orange graph, I forgot the colors. If blue is above the orange, that means blue has more area because it's above the orange, therefore it can gather more area under the curve. And so that is domination. So if your function f of x, if the blue function happens to run above the orange function, then the area, meaning the definite integral for blue, will be a value that's greater, be an area that's greater than the definite integral for g. Let's take a look at some of the examples. We are given and we have the following problem. It says find integral 4 to 1. Okay, that sounds a little unorthodox there when I say integral 4 to 1. Okay. But we do know that integral 4 to 1 f of x dx is not the right order. So the order of integration should be adjusted with a negative sign. So you go from negative integral 1 to 4 f of x dx. And then we come back here. In fact, they give us the answers for those integrals. They don't give us the function, they give us the value itself. So 1 to 4 f of x dx is negative 2. That's negative times negative 2. The same information. Now we have the second question. Find integral negative 1 to 1, 2 times plus 3 times h of x. So we know that we could split this into individual integrals. Pull out the 2 because that's a constant. We're interested in just the variable of integration, so if it involves x, keep it in the integrand. If not, bring it outside the integral. So I'll bring the 3 outside here. So this is f of x, negative 1 to 1, f of x, and negative 1 to 1, h of x. Negative 1 to 1, f of x is 5, negative 1 to 1, h of x is 7. Go back to the given information. It says integral negative 1 to 4. I do have 1 to 4 for f of x. And again for f of x I have negative 1 to 1. So then we could use the additivity property, which says you can go from negative 1 to 4 if you took a break at 1, right? Because that's what we have. Negative 1 to 1 and then 1 to 4. So to answer this question, I split up the interval negative 1 to 1. This was 5 plus, this was a negative 2. So 5 basically 5 minus 2. Show that the value of integral 0 to 1 square root of 1 plus cosine x dx is less than or equal to root 2. Now when you have this inequality, I'm naturally drawn to the max-min inequality. over this interval AB is the integral of f so that's what you get. So I have a way to prove that area of this is basically a triangle, right? So area of this triangle, so which is the area under the curve, is the same as this integral 0 to b x dx, okay? Because that's what we just showed. We kind of defined it to be that way. So let's start with what we know, which is area of the triangle. Area of a triangle is half times base times height. So it's half times base. Base is 0 to b, so it's going to be b. Height, if you plugged in b in your function, right, the height, this coordinate will correspond to a b. So this height is also b, because that's your identity function. Whatever your x is, so is your y. So that's b. So we get b squared over 2. This is what I get from geometry. Okay. Now let's focus on integral 0 to b x dx. Now we know how to find the integral of x dx. We haven't seen how to handle 0 to b, right? The limits of integration. We're getting to that. We'll look at it shortly. But we want to use the original definition, which is limit of Rayman sum. Okay. So I'm going to revert to that, because for now we do not know other ways to handle this. And if you recall, we said this is a plus k times b minus a over n times b minus a over n. Remember that expanded one? This is coming in very handy because I am just using, in this case we could say I'm using the right hand method, the right hand points method. Doesn't matter what method we use because we're just using the a, the k, and the b. So that's limit n approaches infinity, summation k, 1 to n, f of a, the starting point a is 0 plus k times b minus 0 over n. We're going to keep the n as it is. Times b is b, but a is 0. F of bk over n. Now, before we plug in the function, we want to remove anything that does not involve k. We could do that, but I can wait, I think, for the next step. Meaning I was hoping to move the b over n, but not yet. To the denominator. So limit n approaches infinity, 1 plus 1 over n over 1, isn't it? And then when you apply the limit, this becomes 0. So 1 plus 0 over 1, which is 1. you're wondering, well, didn't this take forever for us to get this? We got this like that in geometry. Well, of course, geometry is fun just because of the easy formulas we have, but that's because I gave you a familiar shape. But I also want you to see the appreciation of how we've moved from, Rayman sum and then the limit, and how we utilized older techniques of calculus, or rather I should say the early techniques of calculus, which is applying the limit. And I know this is lengthy, but we're going to get to the point where it's going to be so much easier. Okay, I can kind of break the surprise to you, but I don't know if you will appreciate it. Meaning, I can show you that integral 0 to 1 dx, okay, is x squared over 2. This is how we apply the limits. Oh, this was 0 to b, isn't it? So then we plug in for x as b, and then for the 0 for x. So that comes out as b squared over 2. So we do have a very, very quick way of matching with this answer using integration. But that's a surprise I didn't want to spoil, but now I did. Remove this. So what happens is, we are showing you the origins of integral, and then we will show you the shortcuts to integrals. So you're not going to be doing this forever, but you will need to know how we do this. And so anyway, the point I was trying to make was the area of the triangle is the same as the area of, or same as the definite integral. It's not a coincidence, because we took the long way to show this, and we clearly see that this is working out perfectly as expected. Average value of a continuous function. The definition says if f is integrable on AB, then its average value on AB, also called its mean, is 1 over b minus a times integral of a to b f of x. In the previous lecture, we discussed about the average value as the area over the width. And if you recall, this actually came from rearranging the formula for area, which is length times width, but we saw the length more as a height. Height times. And so height is nothing but the value where the height is attained, right? So that's the average value. So from this, if you solve for height, you will divide both sides by width, and that's how we got area over width. And then this height is nothing but the average value. So we got this information. But if you see this particular definition, it involves the integral. So let me come back to that. Average of f, which is also known as the mean, is still area over width. But now we saw that the definition for area under a curve is the definite integral a to b f of x dx over the width b minus a. So if you again brought out the b minus a separately, that's the same as the definition. So it's not something new. It is the same information, but instead of doing the finite sums, the approximation using upper estimate, lower estimate, or the midpoint rule, instead of doing that, we now have a better way. In fact, instead of approximation, we now have an exact way, which is using the definite integral. So we got that. And based on this, let's look at this problem. Find the average value of f of x equals 4 minus x or negative 2. Okay, now because we could do the same thing using, of course, the approximation, but of course we're not going to do that. So average function is 1 over b minus a f of x dx. That's the definition. Let's plug in all the details we have. 2 minus a negative 2. Be careful there. Otherwise, you'll have 2 minus 2, which will be a 0 in the denominator, making it undefined. that will be totally messy. And a to b is always smaller to the higher value, and it's clearly seen in the way you write your interval. That's the same way you will write your limits of integration. And f of x is square root of 4 minus x squared. Now once again, we haven't, let me write this as 2 plus 2, which is 4. We haven't seen how to evaluate the integral when it has the lower and the upper limits. We know how to handle the integration by itself maybe, but we do not know how this should be done. Therefore, we're going to consider the fact that this square root of 4 minus x is nothing but a semicircle. And it's a semicircle of radius 2. How do we know that? Well, we know the equation of a circle is x squared plus y squared equals r squared, a circle with center 0, 0. R squared would be here 2 squared, which is 4. So y squared will be 4 minus x squared, and y is plus or minus square root of 4 minus x squared. Now the positive root would be the upper semicircle, and the negative root will be the lower semicircle. Together it forms the circle. So here we are talking about the positive root, therefore it's the upper semicircle. And of course, the integration limits also indicate to us that the radius was from, the radius is kind of negative 2 and 2, so its radius is 2 on either side, because the center was 0, 0. So using all these details, if you took the area, now this is this whole thing. This is the area of the upper semicircle. So the area of a circle will be, or rather I'll say area of a semicircle area of the circle divided by 2, isn't it? It's half of the area of the circle. So that'll be half times area of a circle is pi r squared. R is radius is 2 here, 2 squared. So that's going to be, when you clean it up, you get 2 pi. And so that's what I'm going to insert in the step here. That's going to be 1 over 4 times 2 pi, because integral of that indicates that we're talking about the area of the upper semicircle. And so that's going to be pi over 2. The average of the function is. We've come to the end of this particular lecture. What we do notice is we know how to find the average value of a function. The only catch is, let me take you back here, the only catch is when you have to find the integration, because we have not explored all the techniques that we can use. We are going for, in this case, geometry to help us with it. In some other cases, we would go for finite sum approximation, which is kind of counterproductive to some extent, wherein you're not able to use a quicker way to get the answer. But we can still do it. It's going to be lengthy, but we can still do it. So those are the only limitations that I see as of now. But once we kind of reveal or explain all these concepts to you and shortcuts that we can use, then it will become a breeze. Like the next lecture, it will be on the fundamental theorem of calculus. Right there, we will kind of show you how to use the limits of integration. And after that, this will become easy. For now, you'll have to use this roundabout way. But that's about it. So I really hope you enjoyed the concepts that were discussed in this lecture. I will see you in the next one.